Hello and welcome to the presentation on Chapter 9 of the International Levee Handbook. My name is Philip Smith. I work for Royal HaskoningDHV in Australia and I was the lead author for Chapter 9 of the International Levee Handbook. In this short presentation I will give you a flavour of the content of the chapter by way of an introduction to its individual sections and to some of the key issues identified by the drafting process. Chapter 9 sets out procedures and good practice for the design and detailing of levee interventions. The chapter content is generally set out using the principles, issues, methods and examples format, which is in common with the rest of the handbook. Chapter 9 relates directly to many of the other chapters of the International Levee Handbook. The fundamentals which underpin all aspects of levee design are set out in chapters 2, which covers basic concepts for option selection, and chapter 3, forms, function and failure mechanisms. The ongoing processes of operations and maintenance are described in chapter 4, and the completion of levee performance assessments is set out in chapter 5. These represent the stages where the need for design is identified. Chapters 7 and 8 are the toolbox chapters, which respectively include detailed descriptions of the site investigation and characterization processes and set out calculation methodologies relating to all aspects of levee performance. Finally, Chapter 9 clearly subsequently relates to Chapter 10, which deals with the implementation of, by which I mean construction, of the levee designs. Chapter 9 includes 16 subsections. I'll work through each of these individually in this presentation, and for each section I'll set out the main content and provide an example based on one or two of the key issues that arose as part of the writing process. This is a figure that illustrates the complexity of some levee designs. It's important to appreciate that the design of levees does not always start with a greenfield site. There may be an existing embankment of uncertain history and quality of construction. It may have been poorly maintained and may be suffering from varying levels of deterioration or degradation. It may become heavily vegetated, such as the example given in the slide. It should be appreciated that the design process is not just a technical exercise. The designer needs to understand the constraints of a site in order to complete the design. These constraints can be environmental, such as the need for habitat protection, economic, social, and political, as well as technical. It's the job of the designer to devise an arrangement that achieves the project objectives and meets the site constraints. I will return to this particular example later in the presentation. Section 9.1 of the handbook sets out the principles which underpin levee design. They are primarily impermeability, in that levees should be sufficiently impermeable that the flow of water through or beneath the levee during a flood is manageable. Stability, which is of critical importance to levees. They must be stable during a flood, and they should also be designed to be stable at other critical stages, such as the construction stage and the stage immediately after a flood, which is sometimes called the rapid drawdown case. Levees need to be designed to be durable, to resist or accommodate deterioration over a period of time. Resilience. Even if they're overtopped, levees should be resilient during a flood. For example, this may mean that they need to be designed to resist a period of overtopping flow, sufficient for an evacuation of the area behind the levee to take place. The design of levees should also address serviceability, which is the day-to-day operation of a levee, and the designer should take into account the level of maintenance that will be undertaken by the owner-operator in this process. It's important as well that the designer consider whole life planning and sustainability. Levees can undergo severe deterioration during their design life, and the level of maintenance necessary to keep them performing as required can represent a substantial cost, and may also represent or cause a significant environmental impact. In this case, levee designers and operators should consider the whole life needs of a levee and strive to achieve a balance of initial capital expenditure and longer term impacts and costs. In all this, it's important not to forget that levees are like chains. They are only as strong as the weakest link. Levees have many potential weakest links. They are often represented by transitions and changes along the section. It's important that designers give adequate consideration to the detail of these local transitions, so that the weakest link is strong enough to fulfill the design objectives. A key issue that was frequently encountered during the production of the handbook was that of balancing conflicting requirements. In almost every case, a balance has to be found between conflicting factors. These can be engineering, environmental, social, political and economic in nature. But it's important that all of these factors are considered at an early stage in the development of a project, so that they can all be taken into account. Examples include the installation of a flood wall on top of a levee. The wall will provide robust protection in the event of a flood, but will often obscure the view of the river or the sea beyond, and it will have the effect of separating communities from the water for all the non-flood times. Each of the interested parties involved with levee design and construction must give issues like this consideration. Other examples include having a levee which has much wooded vegetation on it. This can act this can have a detrimental effect on performance in comparison with the grass levee, but it will have the benefit of providing it'll have the benefit of providing a habitat which wouldn't otherwise be there. Again, this is an issue that needs to be given clear thought at an early stage of levee design process. The design process starts with a decision that change is needed. This decision may be made as a result of observations during routine operations, operations and maintenance, or as a result of a condition assessment which highlighted the need for repair or renovation, or it may result as or may come about as a result of a strategic planning exercise. Section 9.2 identifies the roles and responsibilities of key players in the design process and sets out their interactions. The key roles are asset owner and maintainer, levee designer and constructor. These role names have been used rather than names that normally relate to the organisations that typically do the work, such as authority or consultant or contractor, because in some cases organisations may work across these boundaries. For example, large organisations charged with levee maintenance will in some cases have the capability to carry out substantial construction works. The use of these names helps to avoid those ambiguities. Section 9.2 also sets out key stages in the design process, ranging from the identification of the need for change through to operating and maintaining the new or modified asset. The section also highlights the importance of phasing larger projects to meet statutory planning and environmental or even technical requirements. Section 9.2 of Chapter 9 includes a number of flowcharts. These have been used to guide readers through the design process graphically. The example flowcharts presented on this slide set out overall design processes of the design of a new asset from inception to operation. That's this slide here on the left. So this flowchart on the left, and on the right, the flowchart sets out the technical design process. These flowcharts are shown in larger images on the next slide that I'll go on to now. The flowchart on the left sets out the key stages in levee design. It's set out in such detail as may be required for a large project and steps through the project definition, the concept design, the detailed design, the construction and operation phases of the design work. Not every stage may be required on smaller projects, and the designer needs to recognise that, that all of these stages are provided for the larger projects, but still some consideration may be given to for small projects, just to make sure that key issues are not forgotten at key stages. The flowchart on the right, over here, sets out the key design steps in the technical design process. This work is broken down into planning and layout stage, the hydraulic and geomorphologic design stage, and the geotechnical and structural design stage. These stages are linked, and in reality the designer may need to go through the stages a few times in order to iterate towards a finally acceptable design that meets all of the design objectives. Predicting the future performance of existing levees requires a knowledge and understanding of ground conditions. And also it requires a knowledge of levee construction and historical response to flooding. Historically, this information has not always been acquired. It's not always been recorded, and it's not always been archived. And in some cases when it had, that information has become lost or redundant. For example, some levees were originally built as agricultural levees, and the information on those was never formally recorded. For others, historical information on ground conditions, design life, performance over flood events may have been recorded, but is not always available to the designer. Overall, it's important that this situation is reversed, and that modern levees when they're designed, record all of the important information on site conditions, design methodologies, and calculation outcome, construction and performance. Section 9.3 sets out recommendations for good reporting practice throughout the key stages of levee design, levee construction and levee operation. A number of key reports and documents are set out in section 9.3 of the handbook. They are the risk register, basis of design report, the site investigation report, the design report, detailed design output, and the operations and maintenance manual. The risk register is an important document which highlights major risks to life and property, to the environment, and to issues such as construction cost, operational costs, and construction program. It records how these risks are managed throughout the design process. It's intended that the risk register should be a living document which records how risks are managed and how newly identified risks are added to the risk register as they are identified. The basis of design report records key design objectives and criteria and environmental and technical criteria that form the basis of the levee design. It's important again that the basis of design report is updated throughout the design process as design intentions become modified or more information becomes known about the site. The site investigation report records all of the site investigation and ground investigations that are carried out in relation to the levee. It includes desk study information and interpretive data that's relevant to the site. The design report documents design assumptions, calculations and conclusions of the design process. It sets the basis for the production of the design documentation. The detailed design output includes the drawings, the specifications, and any other technical data that is required to be given to the constructor in order for the levee to be, or the levee works to be completed. Finally, the operations and maintenance manual is important that it's produced by the designer, as many of the assumptions that have gone into the design need to be passed on to those who will be responsible for the operations and maintenance of the levees. Section 9.4 covers levee alignment and levee layout. Levee alignment is an important early consideration in the design process. For example, as part of the design process, it may be necessary to consider if the levee should be located close to the water, which might maximize the area protected from flooding, or in a setback location, which would give more space for the river. Many factors can control the final solution. Safety, risk, social, environmental, hydraulic, geomorphologic, geotechnical and practical issues are all factors that that will be considered as part of the levee layout and alignment process. The selection of the final alignment will require careful hydraulic and geomorphological analyses in order to balance the risks and benefits associated with new levee construction. Section 9.4 of the handbook discusses issues such as setback levees, no construction zones, vegetation management zones, and interior design drainage systems. The related topic of spillways is discussed in section 9.14 of the handbook. An example of a situation where various levee alignments were considered is provided by the 3 Levees Improvement Authority, Yuba County in California. In this case, the authority opted for a setback levee along the Feather River. In this case, the authority identified the benefits of the setback alignment to be that the ground conditions improved with distance from the river, so foundation conditions were better at a greater distance from the river. It avoided the creation of choke points where the river narrowed and the levees were located close to the river. This had the effect of widening the river channel to improve flow during a flood. Also, the new levee was built at a location away from the erosional points on the existing riverbank. This allowed the river to meander more naturally without affecting flood risk. The levee could also be built offline. This meant that the level of flood risk was not increased during the construction programme. The size of the effective floodplain was also enlarged to make space for the river in flood, and this benefit created a number of potential habitats, which was also seen as a benefit. I'll just point to the location of the setback levee. You can see the river meandering through here with the mouse. The original levee is this small dotted line that quite closely followed the alignment of the river, and the new setback levee was set back considerably further, matter of a number of a kilometre or so from the original levee, and this created more space for the river, more natural habitat, and as a result of this helped to make the levee a more acceptable option for the community. Section 9.5 of the handbook describes how the cross-sectional geometry of the levee is defined. Perhaps the most critical issue here is the setting of the levee's crest level. For fluvial levees, the issues that need to be considered include the risk and the design standard selected for the levee, the results of hydraulic modelling, the requirements for a defined minimum freeboard, or the results of calculations to assess factors such as settlement and wave run-up, superiority considerations, by which I mean constructing levees lower at certain locations in a low-risk place, so that they are preferentially overtop at these locations, meaning that the rivers are, or that the levees are unlikely to overtop at the critical sections, perhaps nearer towns or other occupied areas. It's also important to consider the use of potential spillways. Spillways are reinforced embankments which are designed to resist large overtopping flows. These can be used in combination with floodwater storage zones to create a suitable way of reducing flood risk at other locations. For coastal levees, a number of additional factors need to be considered. These include sea levels, tides and waves, and also storm surges. It's important to appreciate that many of the real devastating floods, for example in New Orleans during Hurricane Katrina and the North Sea floods in 1953, were all associated with substantial storm surges. The design of the full levee cross-section, including features such as crest width, side slopes, berms and so on, follows the selection of the crest level and starts with environmental and operational requirements. For example, the crest should be wide enough so that it doesn't restrict the passage of emergency vehicles, and the side slopes should be flat enough so that they can be mowed or maintained with ease. These characteristics are then modified as the design progresses, for example to achieve stability, and may need to be flattened or adapted from those original conditions that were originally identified. An example of a cross-section which has been designed to accommodate a number of different requirements is provided by the levees of the Natomas Levee Improvement Program in California. Here, the geometry was established to preserve the mature waterside vegetation on the existing levee, to meet technical objectives for safety, impermeability, durability and resilience, and to create habitat without compromising on engineering performance. The combination of these three requirements meant that the levee became considerably more complex than the original levee, and they had incorporated a vegetation-free zone, a new levee with a berm, and an embedded concrete cut-off wall. Section 9.6 of the Handbook covers surface protection of levees. Surface protection is required on levees to protect against waterside erosion against current, caused by current velocities and wave action, and crest and landside erosion from overflow and wave topping. A range of potential measures to protect against external erosion are described in this section. They include grass and reinforced grass, such as turf-reinforced matrices, armour stone, such as revetments, gabions and Reno matrices, which are wire mesh baskets filled with cobble-sized rock fragments, flexible concrete block systems, and soil cement mixing using techniques and materials such as roller compacted concrete. An example of surface protection measures that have been successfully used is provided by the turf-reinforced mattress that was used on some of the levees constructed in New Orleans after Hurricane Katrina. This mattress reinforces the turf to provide greater resilience to overflow without the use of heavy, unsightly or costly construction materials such as concrete. In comparison with grass, it provides greater resilience to surface erosion and to external actions such as traffic loading. Turf-reinforced mattresses are particularly effective in the short term before grass cover on new levees can become well established. Section 9.7, Control of Seepage and Uplift. It's vital that the designer doesn't forget that the primary function of a levee is to provide a barrier to the passage of water during a flood. Water can, however, pass through or over a levee, and if it passes through or beneath the levee, as seepage, it can take a number of forms. These are the flow of water through the levee body itself, the flow of water through the ground beneath the levee, and the flow of water along interfaces between the levee and incorporated structures. Levee designers must anticipate these flow paths and take steps in the design process to inhibit or control the seepage. The volume of seepage transmitted during a flood will generally only constitute a nuisance. However, seepage can lead to levee deterioration through processes such as internal erosion, and this can trigger crest settlement or encourage the formation of pipes, which will be very detrimental to levee performance. It can also raise phreatic pressures within or beneath the levee, and these can have a destabilizing effect. In the worst case, seepage-induced groundwater pressures can induce levee instability. Section 9.7 of the Handbook identifies methods of seepage control and outlines the various benefits and disbenefits of each. The table on this slide is taken from Section 9.7 of the Handbook. It identifies the relative benefits and disadvantages of various seepage control measures. The measures are stabilising berms, impervious layers or barriers, cut-off walls, tow drains and relief wells. For example, relief wells can be used to lower water pressures in permeable subsurface layers, and this reduces the magnitude of hydraulic upthrust, which can then increase the factor of safety against instability. However, the anticipated volumes of water can in some cases be large, particularly for large levees or large river systems. In this case, pumping may be required to effectively lower groundwater pressures. This should be recognised that this is not necessarily a fail-safe solution. So there have been a number of instances where pumps have failed during a flood and the consequences have been catastrophic. It's noted that often the choice of seepage control measures will reflect the nature of the seepage conditions, the nature of the ground conditions, and the volume of seepage anticipated. A problem closely related to seepage is the issue of internal erosion. This is critical for the design of large dams, particularly because dams impound water over much of their design life, and so these internal erosion processes are continuous and potentially very damaging. However, can also suffer from the same processes, but the periods of seepage under which the internal erosion occurs are generally much reduced. However, as the process mainly occurs during a flood, the fact that it's occurring is not always evident, and deterioration experienced by some older levees may not become particularly apparent until a failure occurs. Clearly, from the point of view of stability, observations that are made over a period of time as part of the condition assessment works are very important in identifying these potential problems. A number of mechanisms that are often associated with internal erosion have been identified. These are backward erosion, concentrated leak erosion, suffusion, and contact erosion. Backward erosion is caused by large exit velocities at points of seepage. This can cause erosion, and as this occurs, the seepage point moves progressively backwards beneath the levee, and this can eventually form a pipe. Concentrated leak erosion is caused by a preferential flow of water through a permeable zone within a levee, possibly as an interface between different layers or historical different parts of a levee, or possibly along or through a zone of desiccated material. Suffusion is the washing out of fine particles from the soil matrix under hydraulic gradients. It generally leads to progressive deterioration and may, amongst other things, lead to crest settlement, and this in turn could trigger overtopping flow. Contact erosion is the hydraulic fracture along an interface between a rigid structure, such as a pipe or a culvert, and fill material within the levee. It can open a crack along a rigid structure and lead to a sudden and dramatic flow of water through the levee. This can quickly lead to collapse. It's important that these aspects are addressed as part of the design process so that these mechanisms are unlikely to occur during a flood or during the life of the structure. The figures here illustrate some of the internal erosion mechanisms that have just been described. Backwards erosion, whereby the exit gradients cause erosion at the toe of the levee, and that erosion gradually moves further back underneath the levee. Concentrated leak erosion along a zone within or around a levee, giving rise to erosion and potential settlement over a period of time, or perhaps the formation of a pipe, which could then lead to a rapid collapse, or suffusion, which is the more gradual loss of fine material along a zone of seepage, which may again lead to settlement and leave the levee vulnerable to overtopping. Section 9.9 of the handbook discusses the importance of designing the levee to resist instability during the critical stages of the levee's life. These important stages are during construction. Levees are often built on soft ground, and failure during construction certainly needs to be considered. Stability during a flood. This should include all of the ways in which water may destabilize a levee. This might include the horizontal loading, or it might include uplift under the landward slope or the toe of the levee, which could have destabilizing effects. Stability after a flood. This can be either a rapid drawdown type failure, or it could be as a result of backwards loading. If the levee has been overtopped and floodwater is on the landward side, then that is potentially a situation that needs to be considered as part of the design process. The fourth case is stability during an earthquake. It's not usual to consider an earthquake to be coincident with a flood, but an earthquake is an event that may occur in some parts of the world where levees have been constructed. And if a levee is damaged during an earthquake, it may then be vulnerable to overtopping or failure during the event of a flood in a period after an earthquake. So for that reason, thought needs to be given to the ease of repair of a levee after an earthquake, or the design of the levee so that it is sufficiently resilient to failure during an earthquake. Section 9.9 sets out the important issues that need to be considered when designing levees to resist these failure mechanisms. And these are presented in the handbook in such a way that they're relevant to each of the 4 design situations I've just described. Section 9.9 also sets out a number of potential measures for improving levee stability by design. These are examples of failure mechanisms that I've just been describing. So a failure during construction, failure during a flood, and a rapid drawdown failure. All of these failure mechanisms and these examples are provided within section 9.9 of the handbook. Typical stabilising measures can include modifying geometry, such as flattening side slopes or constructing a berm on the landward side of the levee to increase the toe weight and to reduce the likelihood of slope failure during at any stage. Improving the strength of the ground during construction through natural consolidation or ground treatment. It may mean that some levees have to be built over periods of many years in order to take advantage of this without having to incur the expense of substantial ground treatment works. Can also involve introducing measures to improve drainage and reduce groundwater pressures, either within or beneath the levee. Structural members such as sheet piles can also be installed to enhance stability. In section 9.10, the steps necessary to perform stability calculations for cross-sectional design are set out. This section makes reference to ILH Chapter 7 for site characterization and Chapter 8 for the detailed design methods. Sorry, for the methods of calculation. The key issue for stability determination is the selection of appropriate safety factors for design. Section 9.10 provides examples of global factors of safety or partial factors that are advocated by various different international design approaches. Particular consideration has been given to different approaches adopted by a range of European countries for designing levees in accordance with the new structural Euro codes. Section 9.10 also considers how safety factors are commonly related to different failure mechanisms and to the level of risk. The table presented here is taken from a publication called Urban Levee Design Criteria, which was published by the Department of Water Resources in California in 2012. It sets out a range of different criteria for different levees, different levels of risk. It covers both hydraulic gradients at various parts of the levee and factors of safety for the rapid drawdown case as well as the long-term case. Section 9.11 of the handbook deals with transitions. Transitions are very important for levees. It's been estimated that at least 50% of failures of levees have been caused by internal erosion problems that are linked to transitions. Examples of transitions can include a change in the levee type or structural form. For example, the interface between an embankment, an earthen embankment, and a structural wall. It could be a part buried structure, such as a culvert, or an encroachment, such as a house, which eats into the back of a levee. It could be fully buried structures, such as a pipe or cable that have been buried beneath or within the levee. Or it could be external structures, such as drainage ditches or boundary walls. Section 9.11 provides a discussion on the principles of transition design and provides examples of established techniques for managing these transitions. When it comes to transitions, the detail of the design is very important. External transitions should, as far as possible, avoid details that cause turbulence or lack resilience to overflow. The eye walls that failed so spectacularly in New Orleans are examples of details that lacked resilience. With regards to seepage, the objectives should be to lengthen and disrupt the potential seepage paths by carefully controlling the construction of the interfaces between materials, material types, and different construction elements. This is important so as to prevent seepage and hydraulic separation along these transitions. The example provided comes from the Levee at Caen in France, close to the Gard River, and it was provided courtesy of Thibault Mallet. Section 9.12 of the Handbook described how levees can be designed to manage serviceability problems such as settlement, desiccation and animal burrowing. These issues can cause deterioration of a levee over time, which can lower the standard of protection provided by it. For example, settlement caused by consolidation of soils beneath the levee can lower the crest and cause overtopping of flow. Similarly, animal burrowing can increase the levee's permeability and increase the likelihood of seepage through the levee. Emphasis is placed on proactive assessments of the impact of settlement, desiccation and animal burrowing, but remedial works the importance of maintaining the serviceability issues is highlighted through a discussion on how levee failures can be initiated by serviceability-related problems, such as the settlement causing the lowering of the crest that I've just discussed. Section 9.12 also provides examples of designs and methodologies that can be used to control the damage caused by deterioration. For example, the deterioration caused by burrowing animals. For example, the image on the top here shows a wire mesh that is about to be buried beneath topsoil on the waterward side of a levee. The purpose of this is to discourage the presence of burrowing animals. Sorry, this example has been taken from a levee in Arles in France. In the lower example, this one here, a geosynthetic clay liner has been used in conjunction with a layer of gravel. The composite effect is that the geosynthetic clay liner will reduce seepage through the levee, and the gravel will inhibit the presence of burrowing animals. This example has been taken from a site in Germany where animal burrowing is quite common. Section 19 sets out how the performance of a levee can be affected by selection, deposition and compaction of earthwork materials. It discusses material selection, material specification and provides examples of how both good and poor materials can be incorporated efficiently into a levee. The effect of material selection and compaction on levee performance characteristics such as strength, permeability, compressibility and density are also considered. Section 9.13 provides detailed discussions on levee construction, the use of geofabrics and innovative techniques for construction and ground improvement. It has long been established that earthworks materials are prone to compression settlement when first inundated by water. This is especially apparent in the construction and operation of dams, but it's also a feature that can affect performance of levees. In levees, the compaction of the fill material during first inundation can cause settlement and hence reduce the crest level and the standard of protection that the levee provides. This problem can be overcome by careful specification of compaction requirements. In the example given here, the air voids ratio of the compacted material is controlled by specification. So that in effect, the air voids is limited to 5%, and that means that the material must be within this grey box here. This has the effect of limiting inundation-related settlement. Section 9.14 of the Handbook covers the design of spillways. In particular, it covers hydraulic design to establish the location, the length, the level and the shape of the spillway. But it also looks at the design of the spillway structure itself, which needs to be designed to be resilient to overflow during a flood event. The hydraulic design process for spillways is iterative and depends on both the impact of the spillway and the flood hydrograph and the characteristics of the flow over the spillway itself. Section 9.14 provides principles and examples for many different spillway structures, including massive spillway structures, protected earth embankments, grass spillways, variable spillways, which are erodible, removable, inflatable or collapsible structures, and gated spillways. As an example of spillway design, the figure here shows both the location of a spillway along a levee and the area that is allocated as the flood expansion zone into which the floodwater will go when the levee overspills. The levees are shown here in red, the spillway section in yellow, and the flood expansion zone is located on the left bank of the Rhône at Valabrègue in France. The spillway discharges into the flood expansion zone, which is bounded by both the internal levees and high ground. Water starts to overspill the spillway here during the 1 in 10 year event, and the spillage peaks in a 1 in 50 year event. The maximum storage for this area is reached in a 1 in 1,000 year event. The benefit of having this is it controls flooding downstream from that point by taking a large volume of water once the water level in the river exceeds, in this case, the 1 in 10 year event. The introduction of rigid structures into relatively flexible earthen levees can create interface problems. These can have rapid and catastrophic effects if they're not designed appropriately. And again, the eye walls that failed during the Hurricane Katrina in New Orleans are examples of rigid structures that suffered these problems. This section covers the design of associated crest structures such as crest walls, embedded walls, pipes, conduits and culverts. The section provides critical design principles and it also provides examples of both good and bad practice from history. This example comes from one of the replacement walls that was designed in New Orleans after Hurricane Katrina. This replaced one of the areas where eye walls had previously been installed. It's a much more robust structure than a simple vertical structure inserted into the top of the levee. There's a level of reinforcement to the levee just behind the wall to protect against erosion, and the wall itself is supported on large piles which are driven both through the levee and into the underlying ground. The last section in Chapter 9 is a section on design input into the construction stage. It highlights the fact that the potential for design carries on beyond the initial creation of the drawings and specification, and highlights the fact that the design may need to be somewhat interactive during the construction process. In particular, technical direction may be required on site from the designer to check for compliance with design assumptions, to react to ground conditions encountered during construction, and if necessary to modify or adapt the design, to modify the design if assumed materials are unavailable or if substantially, to monitor earthworks behaviour before, during and after construction. This can be particularly important during the construction of levees on soft ground foundations, where it may be necessary to build the levee in stages, and to do that efficiently requires a high level of interaction between the designer and the constructor on site. Input may also be required to update the design report if changes occur to the design as part of the construction process. Section 9.16, in addition to the design inputs during construction, also considers the use of the observational method during construction as one way of improving the efficiency of construction. And this is the example given on the slide. The observational method is being used increasingly for the delivery of civil engineering projects. It has the benefit of trading conservative design for site observations during construction. So it can have the effect of reducing the cost of construction, but this comes at the cost of a greater level of control and monitoring during the construction process. The use of the observational method for levee design, though, and construction is limited because the design decisions relating to performance during a flood cannot easily be tested during construction. So any designer wanting to use a method such as the observational method for levees must bear this in mind. The observational method, however, can be used efficiently to optimize the rate of levee construction, especially when building on soft clay foundations, as described before. So to summarize, the design of levees can involve a complex balancing act between constraints and objectives. This is a very common challenge that is faced by designers, and I think from my own experience I would say that it's very important that when producing a design, the designer must not lose sight of the principal objective of creating a sustainable barrier to the passage of water. Everything else is important, but it is secondary to this prime objective. Okay, that's the presentation. I hope it's given you a flavour of the coverage of Chapter 9 and will encourage you to investigate the other chapters of the handbook. Each of these have similar presentations. The complete handbook can be downloaded from the CIRIA website. The link to CIRIA's website is given on the current slide. Thank you and good night.